please.
Okay, thank you very much for inviting me to give this talk. I will talk about modeling galaxies, dust, and AGN with CIGALE. And this is done with several people in France and also in Japan and other countries. So I will not present CIGALE, but I will just have a few one slide about the evolution of CIGALE. What we are doing now, at the bottom in purple, I will show later on that we have now some X-ray emission and polar dust with CIGALE that can be used to model the galaxies, AGN, and star formation. So I will talk more about this. And right now we are doing a PhD with I'm advisor in astrophysics, and there is someone in mathematics, where we use deep neural network to modify some of the module in CIGALE, not everyone. For instance, the SFH module, star formation history, and the SSP modules are being replaced by a deep neural network. So this increases speed of CIGALE, but also this one changes cloudy. Well, right now we have tables from cloudy. So that's quite simple in CIGALE, and we developed something more complex using a deep neural network that will add all the capacities, the capabilities of cloudy for the line and the nebula continuum. Also, we are changing the statistical analysis. We have now Bayesian analysis, and we will have something which is a negative imported sampling. So instead of having something where the priors are from a grid, and so here most of your draws are lost, you adapt the proposal along the line, as you can see here, to focus on the interesting part of the information. So these are the two main changes right now for CIGALE. So more scientifically, here is the outline of my talk in two parts. The first part is about modeling dust in the epoch of ionization. So this plot is a very simple one that tries to summarize what are the main physical processes related to dust. So of course, on the bottom, you have star formation. And this means that you have, after that, some stars evolving, supernovae and AGB stars mainly, that produce dust. This dust goes into the ISM and can be destroyed at some time, for instance, when you have a supernovae. You can have also some growth of dust in the ISM, and everything goes back to the molecular clouds that form stars again. This is a box that is the main part of the galaxy, but you also have outflows and exchanging between the galaxies and the intergalactic medium. And this also takes some gas and dust grains out of the galaxy. So we have to take all of them into account when we try to model the galaxies. And the dust cycle, of course. So what we did is that we selected 18 line-membered galaxies with redshift between 5 and 10 approximately. All of them have been observed with ALMA. Most of them have detections, but some have only upper limits, but limits are also something that brings in information. Some of them are lines, C2 or 388 micron. And we have also a sample, a local sample, dwarf galaxy sample at very low redshift and low metallicity. All these galaxies have low stellar mass and low metallicity. And we assume that they are simple galaxies, meaning that we can assume a simple SFH because the universe is young and the galaxies are young themselves. When we try to get something in the infrared for this line-membered galaxy at high redshift, as you can see here, so that's a sample of a few of them. We have sometimes upper limits, that's a triangle, sometimes 1 point, sometimes a few more points, but most of the time we have very limited amount of data available for these high redshift galaxies at redshift 5. So what we would like to do is to densify the information and obtain a more regular sampling in the infrared part. As you can see, we have a lot of data in the UV optical part. So how do we do that? First, we selected the ALMA detected galaxies. So here we have detections, and we have some information on the dust emission. Then what we did is that we use the universe as a redshift. We have a redshift range, and so when for ALMA 6 band, for instance, when you move in redshift, you cover more and more of the SED, from 5 to 9. That's the redshift range we have. So the universe is used as a spectrograph to cover a broader range of the dust emission. If you have two bands, of course, that increases it. And by doing this, we can have some better coverage of the SED. Of course, all the objects do not have the absolute same value, so we normalize at 200 microns here, and we get all the objects normalized at 200 micron, where the dust is supposed to be transparent. And so you get something that we fitted here with the Brennan models, as you can see, with a very nice behavior. And we get a better estimate of, for instance, the dust temperature if you use a black body or anything else. So we have one template that was estimated for the far-infrared detected LBJs. And well, it seems that, sorry, I have a problem with my slides. Yeah. And we applied all of them to the far-infrared undetected LBJs, the one with upper limits. So we assume that all these line-membered galaxies at high redshift, low mass share the same shape for the dust emission. And when we do that, we have something that we can fit with CIGALE, and we can estimate some parameters. So the main one that we'll use here is a specific star formation rate divided by m star, the specific dust mass, and dust divided by m star, and this one, which is the age of the stellar population divided by the tau SFH, which is the extent of the star formation history. Well, this is basically if you assume that most of the galaxies have the same tau for the star formation history, that's the percentage in the star formation event. When this is close to 0, it's the beginning of the star formation event. When it's close to 1, you are at the end of star formation event. So we get a bunch of data, where I will not show you everything here. And we are able to build this type of diagram. So this is a specific dust mass divided by m star, which allows you to have some type of normalization on the dust content. And this is a specific star formation rate. And this is color-coded as this parameter age divided by tau, so the percentage of the star formation event. So before looking at the color, you see that we have less points here than here, which might say that that because we have fast evolution, but it might also be because we are biased in the sample. But well, anyway, looking at this color, so you see that these points here are yellow and move to bluish or purplish, which means that you move in the star formation rate from something early to something late. The other information on the y-axis is that in this part here, you see that we have quite large error bars. Well, actually, there are upper limits for most of them, these ones and this one, which means that these objects have not been detected. So the upper limits are at the extremes of this diagram, meaning that you have less dust in this region and in this region. And here you have detections. We have more dust in the central part. So it seems that objects move in age in this direction, and you have different dust at the beginning, middle, and end. If you want to be sure about this, you look at the IRX, which is infrared to UV ratio, and you see that you have so low dust, yellow or orange here, and bluish here at the central part. And so these objects in central do have larger dust attenuation and larger dust content. So we modeled everything, and we built a lot of models that we fitted them with a chi-square to get the best ones, the blue ones. What we get is that we have dust formation. So this is the function of age on the right and SSFR on the left, which is the same thing here, approximately, given that we have the same star formation story. So we built dust at the beginning of the star formation events. Then you have, well, dust in the galaxies that are detected, and then you destroy dust, but most of them you remove dust in the intergalactic medium. Note that here we don't have any ISM growth. If you have some ISM growth, you go in this direction, which is not consistent with the fact that we have upper limits on the right hand for the age or left hand for the SSFR diagram. So we need to have something removing the dust from these Lyman-Barr galaxies. I need to stress that this is specific to these objects, like these Lyman-Barr galaxies. If you have other objects, you might go in this direction. For instance, in the comparison sample of low metallicity local galaxies, some objects moved here, some objects go here, and this seems to be related to the metallicity as noticed by several works like Asano et al., for instance. So metallicity is quite an important parameter here. So if you have this type of diagram here, which is from Linowska and Mikowski, which is 5.5 to 8.8, what they did is that they show that in this diagram, if you want to have dust explained for this object with different assumptions on the IMF, for instance, you need to have some the dust produced by supernovae. But when you have a supernovae, you have a dust destruction, which is here. And they say that, well, it's difficult to get this object at the top. But actually what we have is something involving. You build dust at the beginning quite fast, so you can reach the upper part of the diagram, and then you destroy dust. But at some point, you have the object at the top here, and you can get up to this. This is a dust-healed dust star. You can get to this upper part of the diagram in this redshift range. Okay, so I move to the second part now, which is modeling AGNs. So there are several papers here as well, by the way. Young et al., Montwichers et al., and Young et al. Again, and also there will be a talk after that. So this is the main paper. And in CIGALE, we added the X-ray component with AGN here, low mass and high mass X-ray binaries, and hot gas. So this is modeled using different prescriptions. For the low mass, high mass, we use Mesquite et al. 18, which is constrained by the age of the star, the metallicity, the stellar mass, the SFR, etc. And for the IGN itself, we use the alpha OX L far UV relation for quasars. Alpha OX is here. That's basically the ratio between the far UV to the X-ray luminosities. And this is a function of LUV. And you see that you have a relation which is a little bit dispersed. This one is from Just et al. That's the one we used. And it's for unobscured quasars, so you need to correct L far UV from the dust attenuation. We see no redshift evolution, and we need to get something which is corrected for all the contribution, galaxy, AGM, and Milky Way. So this is something that we did. We also added something different. Scott are new models, evolution of the Fritz et al. Models, where we have clumpy two-phase torus with a 3D radiation transfer. The energy budget is preserved. We modify the disk acidity to be consistent with the recent results. And we have two main models, AGN1, which is here, and AGN2, which is here. So this is included into CIGALE. And we also had polar dust because we needed to explain some of the dust, and also the attenuation that we have in UV. So this is due following this Liu and Ricky paper. We are not sure about the origin, but we do have an extinction curve and EBV main parameter. And the isotopic remission of the dust due to polar dust is modeled by the gray body at 100 K, where we can have different temperatures here. So these are the main models, type 1 and type 2. So you can see the effect of the EB minus V on the polar dust. For type 1, you have something here that is important, but for type 2, you don't have any difference except in the dust emission. We tested this on different samples, and especially on the NEP, using this Chandra and Giacarino NEP paper with a lot of people from this conference. And so you see the redshift range, 0 to 3.4 approximately, and NH. And of course, the NEP is very interesting because we have a very good coverage of the near infrared plus mid-infrared band, sorry. So we have two objects here in this field. And what you immediately see is that we have an excellent fit here of the Akari data. And we also have an excellent fit of the 1 point from the X-ray here. So this fit here helps constraining all the parameters. I will show that. One of these important parameters is the AGN fraction. And in CIGALE, you can test if your estimate is good or not. So we have the true fraction of AGN, which is modeled by CIGALE. We refit these models and we estimate new ones. And you see that we have quite a good relation for this NEP sample in Yang et al. 2020. Then we had another paper in the XMM XSL field by Mandrishers et al. And we also Yoshiki Toba's talk after this one will talk about this module. So in this paper, we have a redshift range from 0 to 5 approximately. NH is here. And these are the models that we use for this fit. So you can see that for the AGN and Skirter, we use several parameters, and the X-ray modules is controlled here. And this is for the other part, dust, IMF, and SFH. Here we have a number of AGN satisfying the criterion, which are mainly the one with good fits and not too low luminosities. That means something like 2,500 objects. And I compare here what we have for when you use X-ray data and without X-ray data. And you can see that in this diagram, where you have LX as a function of LX data as a function of LX CIGALE, you have a better correlation, lower dispersion at any redshift that without FX. So the X-ray data brings some information that improves the fits. This is the fraction of AGN with and without X-ray data. You see that, well, it's consistent. You have a small difference here for low X-ray luminosity objects. This is the difference between the fraction AGN with and without FX. And so, well, maybe there is a small difference here. With and without polar dust, you might have difference. When you use polar dust in blue here, you seem to find lower fraction of AGN. Well, it's not very different, but you have some difference, which means that using the polar dust modifies the ACD and the way we interpret the ACD. You can also use infrared data, of course, because the AGN emission is quite strong. So here it was tested whether the parameter change without or with and without inertial data. And you see, well, it's maybe not changing except for the fraction of AGN. We didn't test whether the Akari near plus mirror data will change a lot these parameters. But I guess that if I come back to the plot, given the density of data that we have here and the fact that they are in the the rest frame in the near plus mid-infrared range, it will probably change a lot, but that's something that could be interesting to apply. So in summary, my main results. So using the redshift, we can sample part of the rest frame subnanometer SCD of LBGs at the end of, at the epoch of ionization. And so we use the universe to sample this part of the SCD. This was done on a few objects, about 10, but we will extend this with more objects that are observed with all telescope, but probably with JWST, because we are involved in one of the programs here and also in proposals. So if we can get objects at higher or lower redshift, or other ALMA band or no ALMA band, we can cover more of this emission. We interpreted this result as a time of relation seconds, where dust builds quickly here at high SFR, then reach a maximum where you have dust detected, and then is removed in the AGM and destroy. This was done on the LBGs. We will try to get more. But I noticed that Mini-Yun has a nice sample of galaxies that I redshift with data that can be used from Scuba 2. So maybe we can test this model on the other one. And finally, CIGALE evolved to the X-ray. We have some modules that can allow to model this. We didn't mention this before, but the NEP team tried to contact the Eurostar Russian team. We tried to do it also as well as CIGALE team. So we asked, can we use CIGALE XCIGALE on the data? And the answer, well, like they did for before, wait until the data comes out and is published. Thank you very much.
Thank you. Okay, we have only one quick question. I have a question on that. Is it worth some that flux AGN increases polar dust or effects? I'm sorry, can you repeat? I can.
So here, polar dust increases the flux AGN, right? So isn't that the worrisome? So effects too. So I understand if the scatter increases, but it looks like to me it's a systematic increase. So does that mean if we don't have X-ray or the polar dust, then we have systematic underestimate of the flux AGN?
Well, actually, we added this polar dust because when you have AGN1, sometimes you have a very strong emission in UV, and this strong emission in UV was taking part of the star formation, which was supposed to be from the stellar part of these objects, well, even if it's small. And it was not realistic. So that's why we added the polar dust into this object. So yes, it increases somewhat the fraction of AGN. And well, that's what we find. Now, as we mentioned, we are not sure about the origin of this polar dust. And well, is it local, galactic scale, etc.? What is distribution? So that's something new that seems to improve the fits. But well, we need now to understand better what are the consequences of adding this polar dust to the models.
Okay, thank you very much. We need to move to the next talk. So thank you, Denis.
Thank you.